So we have seen the formula, but actually incomplete formula about SAM coefficient. But next, we need to figure out how to maximize the SAM coefficient. According to the previous slide, we know it's about the design of laser cavity, but how to realize it, okay? So this is the method. The bottom one shows the schematic diagram of a curved-length Morlock disulfide laser cavity. It is quite simple, right? You have curved mirror 1, curved mirror 2, planar mirror M1, planar mirror M2. You have a disulfide crystal as gate medium and a central absorber. You have an iris, okay? And you have OC. OC means output coupler. In this case, it's a prism pair. And in lesson 7, we will talk about the functionality of prism pair. It is used as dispersion compensator. But at this point, we don't have to worry about it. So that's it, the simple design of curved-length Morlock cavity. With this cavity, how do we analyze? You have to trace the beam size versus position and versus power, okay? Beam size is a function of position because of diffraction, right? According to the Gaussian beam theory. Beam size will change with propagation distance, okay? But here, because of the curved mirrors, so whenever the Gaussian beam hits the curved mirror, the Gaussian beam parameter will change, right? And you have to include the change inside your analysis. So this is what you have to do. Beam size, say the beam radius W as a function of position Z. It will change because of diffraction. In addition to that, you have to analyze the beam size as a function of power because of Kerr lensing effect. If you can do both, then you can determine the cavity parameters. A lot of cavity parameters have to be determined, such as the aperture position, okay? Where to place the aperture. It's a parameter to be optimized. Because if you place at the wrong position, you cannot have even positive SAM coefficient. That will fail your Morlocking, okay? So position determination is important. Here, it seems that the aperture is placed next to the planar mirror M1. In the future, we will demonstrate why it has to be so. 我会告诉你为什么啊，这个是有原因的，不是乱摆。Okay. You have to determine the gate medium position, which means where to place this disulfide crystal. Okay. You have to determine the distance d prime between the two curved mirrors. If you do wrongly, again, you will get unstable cavity. You cannot have even a laser. Okay. So in the end, we have to optimize the aperture position, gate medium position, and the distance between curved mirrors, such that we can have stable laser, as well as maximizing the SAM coefficient gamma. Okay. Then, linear cavity analysis. Okay, this is the original cavity. D prime is defined here, the separation between the two curved mirrors. What tool do we have? the ABCD matrix you have studied in the Gaussian bin theory before, right? This is a simple review. Say electric field phasor is rewritten as the product of two terms. U is the amplitude. E to the minus jkz means the carrier contribution, okay? And we also know from the Gaussian bin theory that the envelope or amplitude function U is proportional to something like this, e to the minus jk r squared over 2q. Because of the r squared, this is a Gaussian bin, okay? But you see, this is a j, so this is a phase function, right? But in reality, your q is not a real number. If q is a real number, this is a pure phase function. It's not a Gaussian bin. But 1 over q is equal to 1 over z plus jb. You see, q is a complex number. Real part is position. Imaginary part is confocal parameter. They come from the Gaussian bin theory you have studied, okay? And the real part of 1 over q is 1 over r. It is related to the phase curvature. And the imaginary part of 1 over q is lambda over pi w squared. You see w, so it's related to the bin radius, okay? So because of the complexity, this function actually represents a Gaussian bin. It has Gaussian intensity distribution. It has quadratic phase front, okay? And the ABCD matrix tells us the evolution of Q parameter can be easily calculated by this formula. If you have big A, big B, big C, big D, the 4 parameters, actually the 4 elements of a 2x2 matrix, you can calculate the new Q parameter by this formula. Okay, that's the review. Then, what to do? Maybe in the geometric optics, you have known this. A curved mirror, say CM1, can be replaced by a lens whose focal length f1 is r1 over 2. The radius of curvature of the curved mirror divided by 2. It's the equivalent focal length of this equivalent lens. Okay? So CM1 is replaced by this. CM2, using the same skill, you can replace it by another equivalent length with focal length f2 equals r2 over 2. Okay? Then the distance between curved mirror 1 and the planar mirror M1 is S1 preserved here. And this is the planar mirror M1. Similarly, S2 is the distance between CM2 and M2. So in this way, you unfold cavity, original cavity, to a linear cavity. The reason is convenience for analysis. And the separation between the two equivalent lenses is still d prime, which is redefined as f1 plus f2 plus a detuning distance, big delta. F1 就是这一个的焦距 ，F2 是这个焦距。那除了这两个焦距和之外，还多了一个 detuning factor delta. Okay, but don't worry. In the future, whenever you see big delta, it means something related to the separation between two original curved mirrors. Okay. 好，所以第一步我们已经把它换成 linear cavity. What's next? According to geometric optics, you might have known the combination of a lens and a planar mirror separated by distance S1 can be replaced by this one, another curved mirror, whose position, okay, the position of this equivalent curved mirror is away from the position of the lens by S1 prime. Okay, and the radius of curvature of the equivalent curved mirror is R1 EQ. And what are the governing formulas? R1 EQ equals minus F1 squared over S1 minus F1. So if you know the focal length F1, you know the original separation S1. By this formula, you can calculate the equivalent radius of curvature. How about the position S1 prime? It's derived by the scene length formula. 1 over S1 prime equals 1 over S1 plus 1 over F1. So that means the equivalent curved mirror is the image of the planar mirror due to the equivalent length. 意思就是这个东西其实是这个平面镜的什么成像的位置，所以你使用这个 scene length formula 就可以去算相距、物距、焦距之间的关系，就是这个 formula. For the same scale, you can calculate the second equivalent curved mirror. So the original linear cavity is further simplified into a two-mirror cavity. Okay, you see from the original cavity, in 2 steps, you get a very simple two-mirror cavity. That's the equivalent cavity. Then you can borrow the ABCD matrix again. The symmetric factor, this one, and the ABCD matrix of the two-mirror cavity are governed by these two formulas. This will be used in the future. What is the asymmetric factor of the cavity? It's ratio of the two radii of curvature. R1 over R2 absolute square. So it means these two curved mirrors might be different. They do not have to be the same. 可以是不同的曲率半径组成的 cavity. It's okay. But if they are symmetric, you got 1. Big F equals 1. It's totally symmetric. If it is away from 1, it means asymmetric cavity. Okay. But we will see the impact of asymmetry in the future. Second, what is the ABCD matrix of this system? We know in linear optics or geometric optics, a system can be modeled by a 2x2 matrix ABCD. Okay, but what is the 4 elements? Okay, you can use this formula. Starting from curved mirror 1, the impact is represented by this 2x2 matrix. Do you know this? 一个 lens 或一个 curved mirror， 它对应的 ABCD 是这样写，知道吗？这是几何光学学到的。Then propagate for a distance in the air of d. You have another 2x2 matrix. You see a second curved mirror, so represented by the third 2x2 matrix. Then propagation over the distance d in the air, you see the fourth 2x2 matrix. And you have to multiply them together. You got the total matrix, which is this one. Okay, this is the matrix for this cavity system. Then our condition is Q prime equals Q to maintain self-consistency in one round trip. We have repeatedly used the same strategy again and again, right? 对一个 cavity 来说，什么时候会 stable？ 我的高宣并从这里出发，来回一趟会回到原来的高宣并，这样叫做 self-consistency。也就是我的 Q 进去走完一个 round trip， 我会经历这个 2x2 matrix， 乘过之后又回到自己。Okay, so you got Q prime equals AQ plus B over CQ plus D, and it has to be equal to the input Q. then you can use this equation to solve two answers about Q. It's a second order equation, standard second order equation. So you can get two answers here. Okay. Now, to maintain finite bin size, imaginary part of Q can never be 0. Or in other words, your Q parameter must be complex number. It cannot be a real number. Why? Let's go back to here. 1 over Q equals these two, right? If Q is a real number, what happens? 1 over Q is also a real number. Then imaginary part must be 0. If imaginary part is 0, what is W? Infinity. So you must have a infinitely big bin to have a real Q, which is impossible in reality. If you need a stable cavity, this is never possible. So that's why 1 over Q or Q has to be complex number. The imaginary part cannot be 0. Okay. Then, if imaginary part of Q can never be 0, what happens to this formula? 你一定要有虚部，你的解一定要有虚部。你解要有虚部怎么办？根号里面一定要什么 ？negative. So that's why you have inequality like this, because the square root of a negative number has to be satisfied. And if you substitute the representations of A and D in the previous slide, this is your A, this is your D, right? Substituting them into here, A plus D over 2 squared, less than 1, you got this inequality. Okay. And if you substitute R1 EQ and R2 EQ by the T, T is defined here. For R1, R2, and the D, you can get these two inequalities. That means these two inequalities have to be satisfied such that you have a stable cavity. Okay. Then what does this mean? Here I plot the bin diameter versus bias distance delta. Okay, so this is the original cavity. Separation between the two curved mirrors is F1 plus F2 plus detuning big delta. Okay, so the horizontal axis is big delta. Roughly speaking, it represents the separation between the two curved mirrors. When they change, what happens to the bin diameter at this position? 意思就是我观察的位置只放在一个特殊点，就是 planar mirror M1 这里。In fact, you can analyze, you can plot a curve for any position inside the cavity. But here I only pick up one special case. The observation is placed at planar mirror M1, and we observe what is the bin diameter as the separation of the two curved mirrors changes. We got these two curves, okay? And it seems that here and here you have bin divergence or bin convergence. 那它的意思是什么？当我的 separation， OK， 横轴就是我这个 curved mirror 的 separation，tune 到这个位置跟 tune 到这个位置会发生什么事？把它 tune 到这里，我的 bin 在 M1 这里看到的 bin 会怎么样？快速增加，跑到无限大 divergence。If close to this position， 快速减少，变成无限细 convergence。And within this range, this is the forbidden region. there is no stable cavity exists. And within these two ranges, you can have stable cavity, you can have finite bin size. Okay? That's the meaning of this curve. 好，那这个也呼应我前一页的 formula， 不是有两个不等式吗？第一个不等式就是在讲我的 separation 要落在这里才有 stable cavity。第二个 inequality separation 要在这里才有 stable cavity。那这里就是 forbidden， 你不能落在那里。Okay, so now you know if the separation is improper, you cannot have stable cavity, not to mention Morlock lasers， 什么都不会有。OK， 那你一定要操作在这两个区。问题是操作在这两个区的哪一个点最好还不知道，对不对？我们只知道要落在这里或这里，但还不知道哪里最好。Okay, so I emphasize the optimal separation delta remains unknown at this point. It is insufficient. Okay. Any question? Yes.
这张图是用这张图的 curve 是用什么样的东西画？
什么画出来？你说怎么得到这两个 curve？ 这是用这个，OK， 应该这样讲。我刚刚要得到它，我做过2层简化，把 original cavity 简化成这样，我得到这个不等式。你做的简化有好处，你很容易得到这两个不等式，我很容易预测这个 forbidden region， 但是也付出了代价，就是原始 cavity 的每一个位置在等效 cavity 里面就消失掉了。所以如果你要画出这个 curve， 你要回到 original cavity， 就是回到这里没有简化的，然后呢再去做 ABCD matrix 一样做maybe self consistency 这个条件啊，你应该可以算出，在比如说我观察点落在这里，我这里steady state 该看到什么 bin radius， 可以用 ABCD matrix 算出来。好，然后我每改变一个 delta， 我要重算一次，我就可以打一个点，把这些点打完，你就得到 curve。所以相当复杂，你要得到这个 curve， 复杂，很复杂的事情。OK。Any other question? Okay, without doing any mathematics, let's think about which position, okay, any point here, any point here are acceptable. You can have stable cavity. But in terms of post-generation, where could be the optimal position? Just a guess. For example, here, or close to the boundary here. What do you think? Here it means away from the convergence, or here means away from divergence. It's kind of very stable position, right? And if you operate here, it's close to convergence, or operate here, it's close to divergence, kind of unstable position, which would be better for post formation. Remember, to generate short pulse, we need pulse shortening effect. We need self-amplitude modulation, right? And according to our SAM coefficient analysis, it's incomplete, but we have seen the relation of gamma coefficient with respect to beam radius as a function of power, right? And previously we have known the larger the sensitivity, the better for gamma, right? So stable or unstable position is better. Unstable. closer to the divergence or convergence would be better. 因为在这些位置，我的 beam diameter or beam size is very sensitive to perturbation, right? And we need that to create post-shortening effect. If you work here, like it's very flat, then it's insensitive. Your beam size is very stable against the perturbation. It's not good for post-shortening. Curl length more lucky. It's not good for curl length more lucky. 好，所以即使你没有做数学计算，你大概也可以猜出一些性质。Okay, now curl lengthening effect. Previously, we simply omitted the curl lengthening effect. Now we have to take it into account. To analyze the impact of curl lengthening effect, we need to formulate the index profile inside the disulfide crystal. So index n is a function of radius r, longitudinal position z, and relative post position t prime. And its linear index n0 plus index change on axis index change times a Gaussian profile. Because light intensity is also on axis light intensity times a Gaussian profile. And the index change is n2i, has to be proportional to intensity distribution. Okay? But usually, we remodel the Gaussian term as a parabolic term. OK， 所以这个高斯的项呢，近似成一个一减掉一个二阶项 ，Taylor series expansion. OK， but why？ 高斯不好吗？为什么要换成 parabolic？ 有原因啊。但是在讲那个原因之前呢 ，usually if you use simply Taylor series expansion, this factor is 1. But people found if you use 1, the result obtained by using this approximation compared with the original model differs a lot. So they introduce an adjustment factor, usually between 4 and 6, like 5. Okay? If you use an adjustment factor 4 to 6, the result is closer to the result obtained by the original model. But there is no rigorous proof, just numerical simulation you can find. 这样会好一点 but just a number. Okay? And delta n0 is the on-axis index change, which is n2 coefficient times on-axis light intensity. And the light intensity equals laser power over equivalent cross-sectional area, pi w squared over 2. Over 2 is here. Okay? And the reason we use a parabolic model is a Gaussian beam passing through a medium of parabolic index profile becomes a narrower Gaussian. It is still a Gaussian. If it is still a Gaussian, then ABCD matrix technique remains applicable. Remember, ABCD matrix only applies to Gaussian beam. If it is no longer a Gaussian beam, there is no ABCD matrix technique. And if you use the original profile, a Gaussian index profile, a Gaussian beam passing through an index profile of Gaussian, the output is not a Gaussian. But if it passes through a parabolic index profile, the output is Gaussian. So that's the reason they use parabolic approximation. 就是为了让 ABCD 这个简单的分析技术能够继续用。OK。然后呢，为了让结果准确，再加一个 adjustment factor。OK。 So what should we do? A laser beam of power P passing through a low medium will eventually either diverge if your laser power is smaller than the critical power. In other words, your Kerr lensing effect is weaker than diffraction. Okay? Can you get it? Laser power, P, is related to Kerr lensing effect. The stronger the laser power, the stronger the Kerr lensing. You know Kerr lensing is a focusing effect. And linear optics tells us you will suffer from diffraction. It's a divergent effect. So you have two counteracting effects. Kerr lensing for focusing, diffraction for divergent. Okay? If Kerr lensing or self-focusing is weaker than the divergence, diffraction, in the end, it will diverge. But if the laser power is larger than the critical power, eventually the laser beam will be focused smaller and smaller until breakdown or damage. Okay? And the critical power is governed by this formula. Okay, I do not show you how to get it, just a formula cited from our textbook. And if you consider thisulfide crystal at 800 nanometers, the critical power is 2.6 megawatt. So it means in a Kerr lens Morlock thisulfide laser, you have to control your peak power roughly smaller than this number. You cannot tolerate peak power much higher than this number. If that happens, you will suffer from self-focusing and crystal damage. Okay. And the peak nonlinear phase shift in a long medium is determined by SPM coefficient times the peak power. And with a simple derivation, you can conclude that peak nonlinear phase shift is around 1 pi or several pi's. 这个就是在不发生 self-focusing 所造成的 damage 前提之下，你在这个 Kerr lens Morlock thisulfide laser 里面呢，你能够容忍的最大的 nonlinear phase shift， 也就是 peak power 所造成的 nonlinear phase shift。也大概就是几个拍，我们刚刚说这个可能是4到6嘛，那这个呢应该要小于1才不会有 damage， 所以乘起来大概就是4到6个拍左右。That's the maximum nonlinear phase shift you can tolerate. So overall cavity analysis, you have to trace the beam radius W as a function of position Z according to ABCD matrix, and as a function of power P, and as a function of bias distance delta, all by ABCD matrix. Okay, so you have W as a function of Z, P, delta. You have 3 variables, so it's a very tedious calculation. For example, you have obtained beam size, beam radius as a function of position, power, and curve mirror separation, detuning delta. SAM coefficient can be calculated by this formula. Okay, this is the formula we derived before, but we introduce another normalized parameter. 就是我们之前已经看过了嘛 ，W 对 power 的微分在 normalize to zero power 所做的 radius。这里我把 power normalize to critical power. That's it. We got the parameter delta W. We will see the parameter later. Okay, and the SAM coefficient is determined by this formula. Whenever you have delta W, you can calculate gamma. Okay. And it is found the maxima parameter occurs at some planar mirror, either M1 or M2. Okay, so now it is justified why the iris has to be placed next to the planar mirror. Because in that case, you can maximize the SAM coefficient gamma according to the ABCD matrix analysis. Okay. Then, how to optimize the separation between the curved mirrors and the asymmetric cavity parameter. Okay. In the previous slide, we have concluded that position of the iris or aperture has to be next to some planar mirror. So this is a fixed constant. 我们已经决定了 z 要在哪里，就是 iris 要放在哪里，这已经固定了。But beam radius is still a function of laser power and the curved mirror separation. So we can calculate the SAM coefficient gamma as a function of the second variable, delta. Okay, so you got some curves. Horizontal axis is the separation between the two curved mirrors, CM1, CM2. Vertical axis is the resulting SAM coefficient, provided iris is placed next to some curved mirror. Okay, so what can you see? You see when asymmetric factor is very close to 1, such as 1.06. So what does this mean? It means the cavity is pretty symmetric. 就是相当对称的一个 cavity. Okay? You can have a dashed curve. And the characteristics of the dashed curve is you will have very large SAM coefficient, which is good, right? 这个虚线对应的垂直坐标很大嘛，就代表它有很大的 SAM 系数。但是它也有缺点 ，less stable for gamma positive gamma only occurs over a narrow range of delta. So it's like this. Only this range, okay? You see your dashed curve is above 0, positive. You always need a positive gamma. But when your asymmetric factor is very close to 1, this is only true within a very narrow range of delta. So that means whenever there is a misalignment, very slight misalignment, you might fail the Moeller-King. Okay, although the SAM coefficient is pretty large. So a rule of thumb is you have to control your asymmetric factor between 1.5 and 2, such as 1.8. You got the solid curve. In this case, your SAM coefficient might be smaller, but you got a broader range of delta within which you can still have positive SAM. Okay. So it's a rule of thumb. 这是一个经验法则。但是图告诉你原因是什么？你不希望设计你的 laser cavity 在非常 tight 的条件，那么一点点的误差就会 fail 你的 lasing 所以它要控制这个 asymmetric factor. Okay. Do you still remember the definition of this one, asymmetric factor? Remember, we simplify our cavity into a two-mirror cavity, right? The ratio between the two radii of curvature, R1 over R2, is this one. If it is equal to 1, it's a purely symmetric cavity. And here we know the cavity has to be at least slightly asymmetric. That's why 我们看看我们看见的这个 cavity 是不是都不大对称？因为实际上就是需要不对称。OK。The last several pages. Now, previous slide only tells us asymmetric factor has to be 1.5 to 2, but we haven't decided the optimal position of delta, separation between the two curved mirrors. Okay, and we haven't determined the position of the disulfide gate medium. Okay, so we need more analysis. This is a figure cited from the textbook or some research paper. It's a result of numerical simulation and experiments. Vertical axis means the mirror spacing. Okay, actually, spacing between CM1 and CM2, which is F1 plus F2 plus the detuning. OK， 所以你可以想象纵轴在改，就是在改这两个 curve mirror 的间距。What is horizontal axis? The rod position. Rod means disulfide crystal rod. 所以我一边调这两个的间距，一边又调这个晶体在这两个 mirror 之间的位置，我两个都调。然后呢，我会去画什么？我会去画 contours of delta W。Contours means 有点像等高线图哈，就是某一个 curve 就代表像这个 curve 代表上面的每一点都对应到 delta W equals minus 1， 然后第二个 curve 就代表每一点都对应 delta W equals minus 0.5。Okay, and what is delta W? It's related to SAM coefficient, and we know it has to be negative. And the larger the absolute value, the better. Okay, so according to these contour plots, what is the best contour? Remember, has to be negative. Absolute value as large as possible. So which is the best? This is the best, right? Minus 1 is the biggest absolute value, right? So this is the best. And also, this is the best. 不是只有发生在一个地方哈，在这上面就是最好的工作点，这上面也是最好的工作点。OK， 那最好的工作点发生在什么情况下呢？答案是第一个 ，delta is close to the stability boundary, right? You see, along this contour, your mirror spacing is around here. 对过来，就只有这小小的 range 是适合的 spacing， 一样嘛，对过来也只有这一点点的 range 是适合的 mirror spacing. And either case, they are close to this forbidden region, unstable cavities here. So it's inconsistent with what we predict before. The mirror spacing between CM1 and CM2 has to be very close to the unstable boundary. Okay? According to this simulation, it's justified. Second, disulfide rod is deviated from the middle between CM1 and CM2. So the red dashed vertical line means where the disulfide gate medium rod is at the middle. Okay? Middle means here 刚好在 CM1, CM2 的正中间叫做 middle， 这里是正好 middle。But optimal working positions are here. So if this at the middle is bad, here is better, right? So you have to purposely deviate your disulfide gate medium rod away from the middle position. You got bigger SAM coefficient, okay, according to this simulation. And this stuff means experimental results. 所以就是它理论计算完去真的做实验，的确可以得到实验点在预测的附近，证实这个计算是可信的。OK。So in conclusion, what are the cavity design rules? First, we place the aperture at planar mirror M1 or M2 such that you can have strong SAM. here. Okay, this aperture. Second, properly choose the bias distance delta between CM1 and the CM2 such that you have stable cavity and you have positive and strong SAM coefficient. Third, you have to place the disulfide crystal rod asymmetrically, 不可以放在正中间 such that you have positive and strong SAM. And finally, you let the two legs asymmetric. 什么叫两条腿？就是这个距离 CM1 到 M1 的距离是第一个 leg，CM2 到 M2 的距离是第二个 leg。这两个距离要不相等 ，such that you have an asymmetric cavity. Okay, to get good stability, according to our previous slides. Finally, we compare active Moore locking and passive Moore locking. Okay, in lessons 2 and 4. In passive Moore locking, self-phase modulation and the self-amplitude modulation establish a positive feedback to create ultra-broad bandwidth and sometimes highly chirped long pulse. Okay, 在被动锁模里面呢，自相位调变跟自振幅调变会建立一个正回收。What is positive feedback？ 简单说就是，如果你超过平均值，叫做太大嘛，我加码让它更大，这叫做 positive feedback。如果我超过平均值，我就把它减少，这个叫 negative feedback。So what happens in electronics if you have positive feedback? You got oscillators. And how about negative feedback? You have stabilization, 对不对？是不一样的应用。在被动锁模，其实你是一个正回收。为什么？当我的 laser power 增加，我的 SPM 增加，我的 bandwidth 增加，然后我的机制 bandwidth 增加会给我比较窄的脉冲，我不就让我的 peak power 又更大了？然后这个就一直循环下去，这叫 positive feedback. Okay, so the process will continue until the spectrum might be limited by your gain bandwidth. It will stop. Okay. And the output pulse is usually highly chirped because inside your cavity you have self-phase modulation, you have group velocity dispersion. They will incur post-chirp. Okay. How about, So extra cavity dispersion compensator is usually needed to compress the pulse close to its transform limit. 所以就是你出来的脉冲还有压缩的可能，因为它带有 chirp， 只要你能补偿这个 chirp， 你就可以得到更窄的脉冲。This is passive Moore locking. What is active Moore locking? Pulse shortening effect has negative feedback and produces long chirp-free pulse. 在主动锁模里面呢，你是 negative feedback. The shorter the pulse, the less effective of your modulation. So the pulse will cease to be shortened well before limited by the gain bandwidth, right? As we have already shown. And we do not use any phase modulation. So the output pulse is usually chirp-free. Okay? But it also means nothing can further compress the output pulse. That's already the best you can have. Extra dispersion compensator does not help in active Moore locking. Okay, any question? 好，没有的话，这就是 Lesson 4的最后的部分啊。那我们下次就要从 Post measurement 开始啊。